Hello, I'm Bill Kinney. This is video number 44 in a series on arithmetic, algebra, and graphing. It's the last sub-series of that. It's part 3 of that sub-series. On algebra, formulas, functions, and graphing is the sub-series with an emphasis on spreadsheet usage, part 3. Again, we're still not to the spreadsheets yet. That will come fairly soon. So we want to focus on the ideas. We've been focusing on a problem. This problem here, you set the cruise control on the highway and you go 340 miles in 5 hours. How fast are you going and how far can you go in 6 hours and 15 minutes at the same speed? We saw that the speed was 68 miles per hour and the distance you could travel in that amount of time was 425 miles. In the last video we graphed that relationship. Ultimately the relationship was this, that when x is the amount of time that you travel at 68 miles per hour, this formula defines a function that tells you how far you've gone, y, based on x, the amount of time. Take 68 times x to figure out y. The graph is a visual representation of that relationship, a visual representation of that function. It does turn out to be a straight line in this kind of situation when you have just a first power of x here and no square roots or anything like that. It's being multiplied by a number. This is called, by the way, a direct proportionality. The distance traveled is a constant multiple of the time elapsed. Y, the distance traveled, is directly proportional to x, the time elapsed. In direct proportionalities like this, the graphs will always be straight lines through the origin, through the point whose coordinates are 0, 0. There are other kinds of graphs that are straight that don't go through the origin. Those are linear, and those will occur when you add or subtract something to this. And I think we'll have an example for that later. What's the benefit of the graph? Well, for one thing, it's a nice visual relationship. It shows you the nice visual relationship. For another thing, it allows you to estimate, for example, just visually without using a formula, how far you would go if you traveled for, say, 2.25 hours. So 2.25 hours is right about there. Without using the calculator, I'm going to use the graph to estimate, to approximate how far I go in that amount of time. You go up to the graph. The first coordinate of that point would be 2.25. What's the second coordinate? I'd have to go over horizontally to the vertical axis. And I'm not doing this perfectly, but that's supposed to be horizontal. Looks like the answer is going to be somewhere around 170 miles, perhaps. Of course, you can use the formula to confirm that. Use your calculator if you like. 68 times 2.25. Oh, I was wrong in my estimation. I was a bit off, not quite as accurate as I should be. It's 153 miles. So should have been more like this. That's okay that happened. It does illustrate that it's difficult to do. It's difficult to see real precisely what it's going to be. We can turn the question around as well. Here's a question. If you're traveling at 68 miles per hour, how long will it take you to go 220 miles? How long? An amount of time. We want to know x instead of y now. We're going to go 220 miles. How long will it take us? We can estimate it from the graph by going up to 220 and going over as best we can horizontally to the graph. And then back down. I didn't do a very good job again. Let's see, I know 3 is actually at 204. It's going to be more like this. It's going to be a little more than 3 hours. How much more? Oh, again, maybe 3.2 or 2.5 or something like that. It looks like, based on how I've drawn it, it's a little closer to 3.2. Is there a way to figure it out exactly? Yes, you can use the formula. You can plug in what you want to know, which is y, write it up here. The distance traveled is 220. And you can solve this equation for x by dividing both sides by 68. and that'll tell you what x is. It'll be a little bit bigger than 3. The 68th divide out. X is ultimately 220 divided by 68. That's a fraction that could be reduced as a decimal. It would be repeating because it's a rational number, though it's hard to tell that we're seeing the repeating pattern. I don't think we are. It's certainly approximately 3.235 hours. If you wanted to figure out how many minutes, you could do this. About 3 hours and 14 minutes. You could even figure out how many seconds by doing this. About 3, oops, mistake there. 14.117647006 minus 14, not times 14, times 60. 3 hours, 14 minutes, and 7 seconds is how long it would take you to go that distance. What else is the graph good for? Well, it's good for comparison. For example, if we were going, say, 40 miles an hour instead of 68, we would get a different graph. How would it be different? Think about it. Maybe pause the video. Okay, you're back. I'm going to graph another function in green, y equals 40x, that will show the relationship for how far you go based on the time of travel if you're going 40 miles per hour instead of 68. If you plot points, it still goes to the origin, 0, 0. Then the next point you'd plot here would be 140. When you travel for 1 hour at 40 miles per hour, you go 40 miles. When you travel for 2 hours at 40 miles per hour, 40 times 2 is 80. 3 hours, 40 times 3 is 120. For 4 hours, you're going to go 160. Oops, that doesn't look so straight. About like this is the graph of y equals 40x instead of y equals 68x. Y equals 68x is up here, y equals 40x is down here. They're both straight lines through the origin, but they have a different level of steepness. The y equals 68x is steeper than the y equals 40x. If this was a ski slope, the y equals 68 x graph would be more scary than going down the y equals 40x graph. The steepness is measured by something called the slope. The slope of the line is always defined. You might remember that the slope is rise over run. What does that mean? Well, no matter where you are, say I'm looking at the blue line and say I'm starting here, and say I look at the second point over there, you can figure out rise over run by, for those 2 points, figuring out how much it rises, that's called the rise, and dividing by how much it runs, that's called the run. If a graph is going down, the rise is actually negative. And what is that for the blue graph here? I'm taking those 2 points. 272 minus 136 is the distance between the y-coordinates of these 2 points, same as the y-coordinates of these 2 points. 272 minus 136, that's the rise, and the run is the distance here, 4 minus 2. This ends up being 136 over 2, or 68. It's the speed. The slope is the speed. Huh. It's kind of neat. For the other one, for this slope, of the one in green, I guess I should have done this one in blue, the slope would be, again, take any 2 points on it. I'll take the points 80 minus 40 for the difference of the y-coordinates divided by 2 minus 1 for the difference of the x-coordinates. I'm looking at these 2 points here. Giving me 40 over 1, or 40. The slope of that one is also the speed of 40 miles per hour. Think about that. Think about maybe those slopes are often called rates of change as well. Maybe spend a little time looking up the term rate of change online and think about what you've learned here before we go on to the next video.